Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall see bounded sets, accumulation point, and also we shall sketch some region of complex plane. First, we shall see bounded region. I have written definition here. A region S is said to be bounded if there exists region or set is said to be bounded if there exists a real number capital M is positive, such that absolute value of Z is less than or equal to M for every point Z belongs to S. Now, for example, we have seen these examples earlier also. What this mod Z strictly less than 1 represents. It represents a circle with center at origin and radius 1. So, this is clearly a bounded set, because here M can be taken as 1 or any number which is greater than 1 will work for M is bounded. Is a bounded set. Also, if you consider the annulus, say 1 less than mod Z less than 5 is bounded, because here M can be taken as 5, here M can be taken as 1 or any number greater than positive number greater than 1 will work, any real number M, and that is positive. So, here this is also bounded, but the set, if you consider mod Z is greater than say 4, is not bounded, because here we can't find M such that mod Z is strictly less than less than or equal to M, and therefore M cannot be obtained for this condition, and this set is not bounded. Or another example can be considered as not bounded set S is equal to Z such that 0 is less than or equal to x is less than or equal to 1. So, what about this set? This set represents all those complex numbers whose real part is between 0 and 1, but there is no condition for imaginary part, and if you sketch the region of this, then that will be of this type. See, this is origin x, y, and x is between 0 and 1. So, here x is 0 and here x is 1. So, all those complex numbers which lie in this strip, or that means if you consider the line x is equal to 0, then that is y, and this line is x is equal to 0, and this line will be x is equal to 1. So, therefore, this region is unbounded, and that extends up to y takes infinity and y takes negative infinity, and therefore, this is the region which is closed but not bounded, is not bounded. S is closed. Earlier we have seen what is the meaning of a closed set, open set. So, this is an example of the set which is not bounded. Another example of set which is not bounded can be considered as imaginary Z is less than minus 1. So, what is the meaning of this? That is y is less than minus 1, y strictly less than minus 1, and if you sketch this, then that will be, see, this is origin, and we may consider y is equal to minus 1 here, and y is minus 1. So, if you have the line y is equal to minus 1 and it is less than minus 1 means that region below the line minus 1, and it is unbounded because we can't find M such that absolute value of that is less than M. If you consider y as say a greater number, if you take M as any number, say 1000, then you may have y is equal to say minus 1001, and here mod y is not less than m. So therefore y extends to minus infinity here, and thus this is not bounded. So this is the meaning of bounded set and not bounded set. That means we must find m such that absolute value of z is less than or equal to m for every z belongs to the set S. Then the set S will be bounded set. Now we shall define what is accumulation point. Accumulation point of a set, and the definition is a point z naught is said to be z naught said to be an accumulation point of a set S if every deleted neighborhood Z naught contains at least one point of S. Then Z naught is an accumulation point. So that means if I consider this point as Z naught, and this is the accumulation point of the set S if every deleted neighborhood of Z naught contains at least one point of S. That is the condition. S may be this region, see S. So this deleted neighborhood of Z naught, the point Z naught may be anywhere in S or may not be in S. Here the point Z naught is not necessary that Z naught is a point of S, but its a deleted neighborhood contains at least one point of S. For example, if we consider mod Z, if S is, see, mod Z less than 1, then 1 is one is an accumulation point of this set, because a deleted neighborhood of 1 is not a member of this set, but a neighborhood of 1 will contain at least one point of S. This represents a circle with center at origin and radius 1. So we have taken this as this point as 1. 1 means 1 comma 0, and therefore if you draw a neighborhood of this, then here the point will be there, at least one point will be in the deleted neighborhood of 1. Deleted neighborhood we have studied in our earlier lecture. Or second example we may have is S is equal to I power n. N takes value 1, 2, 3, 4, etc. Then what about its accumulation point? Now actually we can see what will be the values of this I power n, and we know I power 1 is I power 2 is minus 1, I power 3 is minus I, and I power 4 is 1, and so on. This repeats, the values repeats. So these are the only possible values for I power n. N is positive integer, and then it is either plus minus 1 or I into I and minus I. and that means if you consider these points in complex plane, see, here is 1, here is I, that yes, and I point is 0, 0 comma 1, that is I. 1 is 1 comma 0, and what about minus I? Minus I is here, this point. The corresponding coordinates will be 0, minus 1, and this is minus 1. So, and but if you consider deleted neighborhood of these points, any one point, then the deleted neighborhood of 1 will be of this type. The neighboring points, epsilon neighborhood of 1 can be considered, and this neighborhood of 1 does not contain a point of this. So, neighborhood of 1 will not contain the point of S, and therefore, this is this set does not contain accumulation point. So, therefore, S has no accumulation point. Now, one more example we may have is accumulation point is also known as limit point. In real analysis also we have studied this accumulation point. Let S is the set I power n divided by n, and n takes values again 1, 2, 3, etc. Now, what about this? So, if n takes greater and greater values, then the denominator becomes infinite, and when the denominator is approaching towards infinity, we know the value will approach towards 0, because this I power n has only these possible values, and this divided by infinite value at the denominator will approach towards 0. So, we have see, I power n divided by n tends to 0 as n tends to infinity. Therefore, the origin is an accumulation point of S. So, this is the meaning of accumulation point, or the points becomes closer and closer to origin, then see, because what we will have is this for n is equal to 1, it is 1 upon 1, for n is equal to 2, it is minus 1 upon 2, for n is equal to 3, it is minus I upon 3, for n is equal to 4, it is 1 upon 4, and so on. And these points all will approach towards 0, origin. And here, if you consider the neighborhood of origin, then there are more points. These are dense near origin. As n becomes large and large, the values will approach towards origin. So, therefore, origin or 0 is accumulation point of this set. Now, next we shall see how to sketch region, given region in complex plane geometrically. I shall write problem, then we shall sketch these regions one by one. I have written here some problems to sketch the sets. Sketch the following sets and determine which are open sets, closed sets and domains. The first is mod of z minus 2 plus I is less than or equal to 1. Now, we shall express the given inequality in usual form, that is z minus z naught is less than or equal to r, so that it will represent a disk. Now, solution for first, that is A. The given set is or the given yes, the region is mod z minus, we shall take minus sign common, then in bracket it will be 2 minus I, and is less than or equal to 1. So therefore, now this will represent, this is of the type z minus z naught is less than or equal to r, and it represents we know a disk with center at z naught and radius r, and that may be closed or open, it depends on this inequality. If it is less than or equal to, then the disk will be closed. So this represents a closed disk with center at z naught is equal to 2 minus I, and 2 minus I means 2 comma minus 1 coordinates, the order pair 2 minus 1. Imaginary real part is 2 and imaginary part is minus 1. Center at this point, and radius is 1. So this is the meaning, and therefore we have to first consider a disk, and it is closed. So we will show it in this dark line. Boundaries are closed, and its center is z naught 2 minus 1, center of the disk, and see the radius is 1. So this is 1 unit and 2 unit on x axis. So approximately we will take like this, and this will be x axis. X axis will touch the disk, and this will be y axis. So origin, this is x. So this length is 1 unit, and the point actually here having x coordinate 2 and y coordinate minus 1. So this is the disk, and it is less than or equal to means all points inside this disk whose distance from 2 minus 1 is less than or equal to 1, means boundary points are also there in this set, and therefore this set can be denoted by this shaded region. Up to the boundary and not outside the boundary. So the shaded region, this is the given set, and obviously this is closed, it is a closed set and not a domain, because by definition of domain it is open connected set. So it is closed set. So in this way we have sketched the first set, mod z minus 2 plus I is less than or equal to 1. Now we shall consider the second one, that is B, and here the given set is mod of 2z plus 3 is greater than 4. We will simplify and again express in the form z minus z naught, mod of z minus z naught, and that we shall write, take 2 common, and in bracket it will be z plus 3 by 2 is greater than 4. Divide both side by 2, and that is z plus 3 by 2 is greater than 2. We have divided both side by 2, and we want the negative sign here, and therefore we shall write z minus minus 3 by 2, and that is greater than 2. So we have again written this in the form of z minus z naught, z minus z naught greater than r, and it will represent it will because this is greater than 2, it will represent all those points whose distance from this point minus 3 by 2 is greater than 2, and therefore this represents all points in the complex plane whose distance from z0 is equal to minus 3 by 2, and that minus 3 by 2 means its imaginary part is 0, is greater than 2. So that means these will be the points which are outside the disk, whose center is minus 3 by 2, 0, and radius is 2. So that is those points, it represents the points outside the disk of center at minus 3 by 2, 0, and radius 2. Now we shall draw the figure. See, the center is minus 3 by 2, 0, and the radius is greater than 2. I shall draw the figure here. So first, see, this is greater than the mod. It is actually mod z minus 3 by 2 is greater than 2, and therefore this set will be open set because its boundaries are open, and we shall denote it by broken circle, broken boundaries. So this is the center, and suppose the radius is 2, and you see it is minus 3 by 2, 0 is the center, means on the negative x axis, and the x axis will pass through this center. This is z0, minus 3 by 2, 0, and its radius is 2. So therefore the radius of this is 2, and the y axis will be at some point here, because this is 1.5 distance, and the radius is 2. So this is origin, this is the point, say 0.5, this distance is 0.5, this is minus 3 by 2, total radius will be 2, and all those points, this is greater than 2, those points which are outside this disk, or it represents the points outside the disk, and that can be shown by this shaded region. The shaded region represents the set, the given set. Now what about this set? This is open set because it is greater than 4. Those greater than 4, and here that means it is this is equivalent. This is equivalent to this, and if you see this, then those points which are at a greater distance than 2 from this point, means from this. So this distance is 2. This is 2, and those points which are greater than distance 2 will be in this set, that is outer points, all outer points, and this is actually unbounded set, and this is open set because its boundaries are open. Greater than 2, that means here the point, this will be an accumulation point, these points will be. So it is open set, and therefore it is a domain. It is an open set. It is a domain. By definition, non-empty open set which is connected, any point are connected because we can join it by finite number of line segments that we have seen in our earlier lecture. Now the third example, that is imaginary z is greater than 1. It is easy. Now you see solution for the third. Imaginary z means y greater than 1. The given set is imaginary z greater than 1, that is y greater than 1, and therefore the figure here is simple. It is unbounded set, and if you consider the complex plane, y is equal to 1 is this point, y x is 1 is this point, and therefore y is equal to 1 is this line, and all those points which has y coordinate greater than 1 will be these, and so this will represent, the shaded region will represent imaginary z given set, imaginary z greater than 1. It is open set. It is an open set, and it is a domain. Now the next one we shall see D. Here the given set is 0 less than or equal to argument z is less than or equal to pi by 4. This is the condition for z is not 0. Condition for argument of complex number, all those complex number whose argument is between 0 and pi by 4, including 0 and including theta is equal to pi by 4. That is, now see, this is x axis and y axis. Theta is equal to 0 will represent this x axis. Here the theta is 0, and we know the angle made by the vector z with this positive x axis is theta, and therefore theta is equal to 0 is this line, and theta is pi by 4 bisects the first quadrant. So this is theta is equal to pi by 4, and this is theta is equal to 0, and this angle is pi by 4. So therefore all those points which lie in this segment is the set whose argument is between 0 and pi by 4, but origin is excluded from this, and that means this is the set up to this. And so on. So the shaded region is represents the set, given set, and here you see this is a closed set. Whether it is a closed set, it will not be a closed set, because z, the origin is not in this, and for that purpose it is not a closed set. If the origin is included in this, then it will be a closed set, because the definition for closed set is it must contains all its accumulation point. So since z equal to 0 does not belongs to this set, is that is the origin. Origin is not in this set. It is not closed, and it is not also open, because it involves these boundaries. Theta is equal to 0 is included in this, theta is equal to pi by 4 is included in this. It is not open, because if you consider a point on this line, theta is equal to pi by 4, its neighborhood, however small it may be, will not be entirely in this. Some part will lie outside this, and therefore this is not open, and this is not closed because origin is not there, and therefore this set is, it is neither open nor closed. It is not a domain. And so thus we have seen how to sketch the regions in complex plane, or how to draw a region for given set. Now this for this it is simple, or we have seen this earlier also. Imaginary z is 1 means y is equal to 1. It is simply a line, y is equal to 1. You sketch the region for this. So in this way we have seen bounded point, region, accumulation point, and how to sketch a region. I hope you understand this. Thank you for watching the lecture.